Right, hello everyone. It's my pleasure to introduce to you Kyle, who will be speaking about the Kähler-Ricci flow. So Kyle's in the process of completing his PhD at ANU. Take it away, Kyle.
Thank you. Paul asked me to give a talk, and I'm really not a Richie Flow person. I'm really it is second order estimates. That's what I do. I do the Schwartz lemma. That's really what I'm all about. But I started in the Kähler-Ricci flow, and I wanted to talk about, instead of the kind of classical way to get into it, talking about Kähler-Einstein metrics and stuff, which has been beaten to death, I wanted to give a more modern introduction, maybe like concerning a more modern problem. So that's the Wu-Yau theorem, and yeah, the first of these lectures is really going to be initiation and propaganda. So I have a lot of opinions on how things should go, and that's really what I'm going to try to indoctrinate everyone here. Ben has he has heard this propaganda one too many times. He probably thinks of it as bullshit, but it's nonetheless, I think, important to talk about. And then in the second lecture, that's where we're really going to get into the full details of proofs and things like that, so that you can then start recruiting people into the cult that we're trying to form. So just to put things into context, this is the kind of historical timeline that I see things, at least. Yeah, these are totally heuristic. Do not take, the curves are not legitimate in any sense. But what we see is that around the turn of the 20th century, or the late 19th century, where Riemann is starting to form things, and there's the definition of a complex manifold, and manifolds are starting to be formalized. That's kind of this first period. Now that was actually motivated, we had a definition of a Riemann surface and things before we even had really the proper definition of a manifold at that time. So there was like function theory in one complex variable was kind of a motivator for that. And then that really took off, and it kind of peaks. And this, what I mean by function theory, is like several complex variables, holomorphic maps and several complex variables and so on. That kind of peaks soon after cohomology appears, which is about the end of the war, really. And so that kind of has still going, but it's not really the main flavor of complex geometry. Cohomology is really the era which we're now kind of on the tail end of, in the sense that cohomology has been this big machine that has been extremely fruitful and continues to be fruitful. And that has what has really led to the power of Kähler geometry. Kähler geometry is where you have a metric, but you also have access to this big machine. And so what I'm going to try to convey today is why that is so successful. So we'll see why it is indeed successful, and why the Wu-Yau theorem, which is a statement about a curvature constraint which is non-cohomological, but gives you a cohomological curvature constraint, why that is kind of so surprising, and how this is really the trend we need to be heading towards. So we're backing away from cohomological constraints because we've kind of developed that theory quite well, and we need to start looking at how we can deal with problems which when we don't have cohomology present. So that's the kind of propaganda and stuff. That's the narrative. Okay, so let's just start with a reminder, because I'm sure everyone knows complex manifolds to some extent, but let's just remind ourselves. So everything is going to be assumed to be connected, second countable, take sufficiently nice conditions as much as you want. The point is that a complex manifold is a smooth manifold whose transition maps are holomorphic maps between open subsets of Cn. So this is the If you want a definition of a holomorphic map in several complex variables, take it to be a smooth map such that in each direction, d bar, meaning the anti-holomorphic derivative, vanishes. Or you can say in the neighborhood of every point, you have this power series expansion. So, okay. So just some standard examples of complex manifolds are complex Euclidean space. That's in a sense the silly example. And Pn. So you take Pn is always going to just be complex projective space. These are just the two kind of, the affine and projective side of things. These are the key examples. So the first thing, if we're not initiated into the field, is we need to understand how much they are more rigid than smooth manifolds. And the kind of prototypical example of this is the failure of the Whitney embedding theorem to hold in the complex or holomorphic category. So we know that any smooth manifold embeds into some sufficiently large Euclidean space. So it's natural to think, okay, can we kind of try to embed holomorphically every complex manifold inside some C? So if we take, let's say, X to be some compact complex manifold, we can ask whether it, for instance, take Pn or a compact Riemann surface, we can ask whether that embeds holomorphically into Cn. Then what we'll get is the coordinate functions will restrict to our compact manifold, and then we'll get, since by the maximum modulus principle, they're just forced to be constant because you'll have these maximums occurring. And so you can't have a compact complex manifold embedding holomorphically to some complex number space. So those which, let me just remark that those complex manifolds which do happen to holomorphically embed form an important class, and those are the Stein manifolds. These are a kind of, in terms of the landscape of complex manifolds, they form a quite important class. They're certainly not compact by the previous discussion, and these generalize these domains of holomorphy. So if we go back to the historical narrative, kind of these were things that people cared about quite a lot. Grout, Riemann in the, from the 60s, 70s, and so on. Understanding what Stein manifolds were was quite a big deal. But we understand them reasonably well now. Okay, so what we want to understand is how this presence of a complex structure interacts with, really, when I say geometry, I mean the metric here. So if I have some curvature, how is the presence of a complex structure improving that?
Kyle, can I interrupt?
Absolutely.
You said, okay, there's two models, right? Affine, projective. One is non-compact, the other one compact. And of course, compact manifolds, well, you can't embed them in CN, right? What about into projective space?
We're going to get there. That's, of course, Kadar embedding and
forget my question.
Yeah, just be patient. The narrative is carefully constructed. Okay, so the presence of holomorphic transition maps and so on, that's expressing compatibility with a metric is not so clear. So we want to introduce an object which is more amenable to this kind of interaction. The way that that's done is through what's called an almost complex structure. So if we take a smooth manifold of even dimension, we can look at the tangent space. We can define a map on each of these tangent spaces which squares to minus the identity. And any even dimensional smooth manifold has such a thing on each tangent space. That's just given by standard linear algebra. But we want to know whether that thing glues together to actually get a endomorphism of the tangent bundle. So you can all glue them together to get this section. A kind of nice thing that I wish was pointed out to me a long time ago. Maybe it was so obvious it wasn't worth pointing out, but like a nice way to think about an almost complex structure on S2 is to take the cross product with the normal. The cross product will produce a vector which is orthogonal to the ones you started with. So if you want to rotate by 90 degrees, you can just take the cross product with the normal vector. It's kind of it's a nice example. So one can show that a complex manifold is certainly an almost complex manifold. But one thing to point out is that almost complex manifolds are easier to understand in the sense of when there is such a thing, because the definition is given in terms of the existence of a section of a certain bundle. And we have a big, powerful machine to understand such things. That's in terms of characteristic classes, homotopy theory, and cohomology theory. So essentially, you can detect almost complex structures, well, comparatively much better, since there is this big machine that we have access to. And one can use this big machine to show that the only almost complex spheres, for instance, are S2 and S6. What's also interesting is that the only almost complex manifolds which are known to be not complex exist in dimension 4 at present. There's no higher, and in fact, Atiyah's failure to prove the Hopf problem that S6 has an integrable complex structure was that people don't believe that the invariant he constructed for higher dimensional manifolds was actually legitimate. There's no invariance. Okay, so almost complex manifolds are not complex in general. The obstruction is measured by this hideous Nijenhuis tensor, which is, in my opinion, really the bottleneck to understanding the problem. The problem that differential geometers have, if they look at this, they say, yeah, it makes perfect sense. We understand this fine, and don't proceed to try to understand it any better. And I think if we understood the Nijenhuis tensor a little better, we might be able to attack the Hopf problem a little better. It should be mentioned, and Ben knows this certainly, that I waste a lot of time thinking about S6. So that's why I have all these opinions as well. Sorry. So the Newlander-Nuremberg theorem states that exactly if this Nijenhuis tensor vanishes identically, then that's equivalent to the existence of local holomorphic coordinates. So if we have an almost complex structure such that the Nijenhuis tensor is vanishing identically, that is what could define a complex manifold. Okay. So easy exercise to show that every almost complex structure on a Riemann surface, basically the only plane you have is U and JU, for instance. And so if you plug that into the Nijenhuis tensor, that will just vanish identically. So if you have an almost complex structure on a Riemann surface, it's going to be integrable. Okay, so I just want to talk about Hermitian forms. So if I take some vector space B and take this positive definite Hermitian form, I'll write it in terms of its real imaginary parts. Then the real part is a positive definite quadratic form, and minus the imaginary part, well, I don't need minus here in this case. Omega will be a non-degenerate 1,1 form. Let me just emphasize that form is type 1,1 if it satisfies this orthogonality condition in a sense. So when you plug in J into each entry, it's equivalent to not plugging in J at all. Okay, so what we'll do is we'll let H denote the space of Hermitian forms on the tangent bundle, on each tangent space and then smoothly varying. We'll write it in a similar way to what we saw before. And what we can do is we can think of the almost complex structure as a linear embedding from R into the space of 1,1 forms, which is given by inserting J into the first entry. That allows us to take our metric to the symplectic form. Well, the metric into the form, I should say. It's not necessarily symplectic. So now if I impose this linear constraint by declaring that the exterior derivative of this 1-1 form vanishes, then that defines a Kähler structure. So it's more illustrative to give the following definition, however, namely that one can express the Kähler condition as the almost complex structure J, which is underlying the Kähler structure, is being parallel with respect to the Levi-Civita connection. This is probably the most enlightening of all the definitions because it expresses the compatibility between the structures. Yeah, there are many ways to do it, and each talk I give, I try to do it a different way. So I thought I'd do it with this linear embedding this time. I told Ben about this the other day, but when I was speaking with Yaniv Rubinstein, he said you should never give a definition the same way. You should try to give a definition in the most obscure way possible so that people who know the definition still pay attention. And so progressively trying to think of more obscure ways to give the definition of a Kähler manifold. Okay. So if X happens to be compact, then the Kähler condition is going to force omega to be represented. So d omega being 0, that's going to imply that it represents a cohomology class in the second de Rham cohomology group, and non-degeneracy, compactness will ensure that it represents a non-trivial cohomology class. So for instance, if the second Betti number was 0, then we won't have a Kähler structure. Now, a cohomology class in the second de Rham cohomology group is going to be referred to as a Kähler class if it can be represented by a Kähler metric. Now, I should mention that this is a completely nonsensical statement. A metric doesn't represent a cohomology class, but this is the kind of imprecision that Kähler geometers, I guess everyone in Hermitian geometry even abides by, which is that there's no difference between the metric and the form. So we just use it, interchange them without any consideration, without telling anyone, and that even is infiltrated into the textbooks. I remember learning this initially and being quite confused. Okay, so let's just give some examples. Again, I have a nice little example is just take the Euclidean metric on Cn. More important, so that's going to be an example of a Kähler metric. If I restrict to a complex submanifold, then that will inherit the Kähler structure. And that actually has an important implication because now it tells me that all Stein manifolds are Kähler because I can holomorphically embed a Stein manifold into Cn. So I can restrict the Kähler structure and it'll therefore be Kähler as well. So many complex manifolds do not support Kähler structures. Even if they happen to support a Kähler structure, they can of course support a non-Kähler structure as well. So the standard example of a non-Kähler manifold is Hopf surface and so on, which because its second Betti number vanishes, the argument or the discussion from before shows that it doesn't support a Kähler structure. This is kind of the boring example. This is the standard one that everyone knows. So
why does the argument tell you that it has to be a non-trivial class in cohomology?
It just got to be. It's a compactness is used there. So for instance, it's also non-degenerate. You need non-degeneracy there. But of course, I could Cn would give me a clear example of it representing a trivial cohomology class. Yeah. That was a fact that so that was something that also I learned that too late. You know, it was almost embarrassing how long it took me to, because I didn't even think of CN. And so I was just asserting this blindly. Yeah, I could go on for days with the number of things that I should know, but it took too long to learn. Yeah. Okay, let me speak about a little more interesting example. So let's suppose that S6 supports a complex structure. So it supports an almost complex structure, but let's suppose it supports an integrable one. So it happens to be a complex manifold. So since the second Betti number of S6 vanishes, certainly non-Kayla. And there's this result of Campana, Demailly, and Peter Nell, which says that it doesn't even support non-constant meromorphic functions. So the algebraic dimension of it, which is to understand to be the number of meromorphic functions, happens to vanish. And this makes it rather, so there are a number of facts that we know about S6, but this in particular kind of says that it's quite far away from what we understand. For instance, if it was projective, its algebraic dimension would be equal to its dimension. This is kind of, it's quite far away from this. So, okay, it's a partial example because it's a hypothetical example.
So that's a strange statement, right? Because you mean for any almost complex structure, there's no non-constant meromorphic functions. Okay.
Yeah.
So this is purely topological somehow.
Yeah, it's a complicated proof though. It's actually true. It's actually true for any threefold with second Betti number equal to 0, I believe. So it's actually threefolds with second Betti number equal to 0 that are quite hard to understand. And so again, to fit it into this narrative, it's because cohomology is not at hand. You know, S6 is so hard because most of its cohomology groups are 0. So every kind of, if you look at kind of any theorem about S6, it's really a reduction to something about cohomology. And then you just say, oh, I can't support that because the Betti numbers are 0 and so on. But why this theorem is also quite interesting is the following. So if I blow up S6 at a point, this picture is just a generic blow up picture. It's not of S6. But if I blow up S6 at one point, the total space of that blow up will be diffeomorphic to P3. And I can apply some general nonsense to say that, okay, the algebraic dimension of this blow up will also be the algebraic dimension of the base. And so what I'm seeing is the algebraic dimension of these P3s that I'm getting is going to be 0. But that's certainly not the standard P3 because the standard P3 is projective and so it should have algebraic dimension 3. So if S6 has a complex structure, so it's actually a complex manifold, then you get exotic P3s. And you know, it's a matter of opinion whether you think such things should exist or not. But people are typically under the belief that Pn is quite rigid, so such things shouldn't exist. Personally, I don't want to make this talk just about my opinions on things, but I hope it does exist because it would show that there's a class of manifolds we're just really confused by. And those would be interesting. Okay. So I should mention that Pn is Kähler, and if I look in a certain affine chart, Pn, I can write the Fubini-Studi metric on it in terms of this in coordinates like this, given by dd bar of log of the sum of squares. Now, since submanifolds of Kähler manifolds are Kähler, I get that projective manifolds are automatically Kähler. Now, not all Kähler manifolds are projective. However, if you take a sufficiently generic complex torus of dimension at least 2, then you can can express a condition in terms of the lattice here. And if you want it to be projective, then you would get some condition on the determinant. The determinant would be 0. You form a matrix associated to this lattice. Then the determinant of that thing would have to be 0, say, and then you show generically that's not the case. So that's the kind of, it's not an argument, that's just kind of the heuristic on how this thing is approached. To see when something is projective, this is Ramiro's question. We need to talk about ample line bundles. So we'll say that all line bundles are understood to be holomorphic line bundles. The line bundle is said to be ample if the sections of some sufficiently high power of it give you a holomorphic embedding into some Pn. So, for instance, if I look at the tangent bundle of a Riemann surface, say of genus G greater than or equal to 2, then if I tensor that sufficiently high, then the sections of that will give me an embedding into P. I think actually the n in which you can embed it is like a whole area of research, like the smallest number, and what these k's can be. Yeah, that's obviously not my area of research. Okay. So if we have a line bundle, we can define a Hermitian metric to just be a smooth family of Hermitian metrics on the fibers. And the most important example of a line bundle associated to a complex manifold is aptly named the canonical bundle. And that is the top exterior power of the cotangent bundle. So this N0 I haven't really explained, but an N0 form is where you have only DZ, so DZ1 through DZN. You don't have DZ bars, for instance. So if I then look at a Hermitian metric on such a thing, then I would have an N0 part and then the 0n part. So I'd have a top degree form, and that would give me a volume form. Okay, so if I have a Hermitian metric on a line bundle, then the curvature form of that Hermitian metric is going to be given by this formula, IDD bar log of H. And this defines a closed real 1-1 form. We'll say that a line bundle is positive if there exists a smooth Hermitian metric such that the curvature form is positive. And I say positive in the sense of forms because I can write this in terms of locally some matrix, and that's a positive definite matrix, for instance. If I look at the dual bundle equipped with its induced metric, then what we observe is that the logarithm will force the minus to come to the front. And so we see that the curvature of the dual line bundle will be minus the curvature of the original bundle. So in particular, line bundle is negative if its dual bundle is positive in the previous sense. And of course, standard theory. Since is this the right ordering? Yeah. Since the curvature form is closed, again, it's going to represent a cohomology class in the second Durham cohomology group. And the cohomology class represented by the curvature form is referred to as the first Chern class of the line bundle. Okay, so this is probably one of the few calculations we're going to do today. And if someone has a very nice proof of this fact, like a kind of, I personally don't like this proof, but this calculation I don't like. So if someone has like a really nice argument, please do tell me. So I can define the curvature tensor of a Kähler metric by this formula where gamma is the Christoffel symbols. What I say can because I'm not saying that's how you should do it, but for this purpose, it's perfectly fine. I know so I can use Kramer's rule to deduce the following formula. So if I have a Hermitian matrix which is invertible, and the terms in the matrix depend on T, then I can differentiate the determinant and I get an expression of this type. Now, if I apply that to the Ricci curvature, as a contraction of the curvature, then I see this argument here. So that's just the contraction. Then via this formula here, I obtain this, but that's exactly just the minus the second derivative of the logarithm of the determinant. It's clear why I don't like this argument. It's not, I don't know, I don't find it very enlightening.
Why not? Sorry, I think it's.
The statement is rather profound that the Ricci curvature can be represented as the curvature form of a Hermitian metric on the canonical bundle, on the anti-canonical bundle, I should say. The proof given here is compute it. You know the formula already. Oh, it kind of comes out. No, I don't like that. Even if the proof was more complicated, I would kind of still prefer that than this kind of yeah, I don't like this kind of, it's like a naive calculation that kind of just, oh, it falls out.
Well, even the interpretation of the term on the right is a bit odd for a Riemannian geometer, right? So the determinant of G is not something that makes sense independent of your coordinates. And so there's already something implicit here, which is that this is something that makes sense for any set of holomorphic coordinates and gives you something tensorial.
Mm-hmm. Mm-hmm. That's interesting. Hang on. So, well, yeah, determinant of G does, depends on the coordinates, but this.
I mean, it's a function in any chart, but as a function on the manifold, it makes no sense, right?
Yeah, so this is definitely a local expression. But is there something?
I mean, up to scaling, it's well defined, Ben, right? And then because you take logarithm, then the scalar goes away.
In a Riemannian manifold, you can just choose your coordinates and make determinant G constant, right? So that, I mean, it's something about the holomorphic coordinates that makes it different.
But I mean, it's also, I think, because you see these density functions or determinants when studying Ricci curvature a lot, right? And I think at the heart of, I mean, if you look at the, I don't know, how you define, say, spaces with positive Ricci curvature in a synthetic way, say for metric spaces, right? I don't know if you're familiar with this, but you need to throw in not just a metric distance, but a measure, right? And to me, at the heart of that sort of work, which of course I don't understand, is this silly computation, you know, that the determinant, the derivative of the determinant involves, you know, the trace, and somehow Ricci is a trace, and so that's why Ricci is related to volume densities, right? And it appears a lot when you see Ricci curvature. For instance, the recent work by Bamler on weak Richie flows and the way he interprets the Richie flow as a synthetic object, right? The key thing is you forget about your smoothness and you just retain your metric and then some heat kernels. And those heat kernels are just, you know, probability measures. And why measures are enough? Well, I mean, because you want to see what happens with Richie. And I don't know, that's why I kind of like seeing this computation, because it sort of lies at the core of a lot of understanding of Ricci curvature that we have, you know, that you need to play around with volume densities. But I see why you want some more cohomological reason.
I do definitely want a cohomological reason. One thing that comes to mind is that's 100% that obviously, you know, volumes are, and determinants are really at the heart of the Ricci, but that's the heart of our present interpretation of the Ricci, which could be that we're all just kind of sitting in this echo chamber of dogma, and we just haven't been enlightened to the higher perspective. But no, 100%. Yeah, I can see why people would value this. I just don't. It's exactly because I want this cohomological proof, really.
I will have some time to convince you when you come over.
Yeah, exactly.
So why
more than
can't this
happy.
be defined on a Riemannian manifold? I mean, it won't be Ricci, obviously, but isn't this fine?
Ben, do you want to?
Well, I mean, it depends what you allow your coordinates to be. If you allow arbitrary change of coordinates, then you can just cook up something where the determinant energy is just constant equal to 1, for example.
Yeah.
So, but if okay, as was pointed out, if you have a measure, then you can make sense of this as the function would be then the density with respect to a measure, and then you can do these computations. Yeah.
Yeah. Okay. Yeah, that makes sense. Thanks.
Okay, so we're convinced of the formula. So in particular, we see that the Ricci curvature can be locally expressed in this form. So I've changed now the determinant to the top exterior power of the form, and that elucidates the important fact that the Ricci curvature can be interpreted as the curvature form of a Hermitian metric on the anticanonical bundle. The anticanonical bundle being the dual of the canonical bundle. That is really this is one of the key achievements of the Kähler world. This is what makes, I mean, we have Hermitian geometers in the audience. Life is hard when you do not have this. And really, if you can reduce to this, then you end up back in the nice God-fearing Kähler world, and you can kind of get all your theorems again. So the Ricci curvature is really a cohomological object, and it really it gives it represents the first Chern class of the anticanonical bundle, but you can go between this metric property and the cohomology and positivity of this bundle interchangeably, and that's really kind of this Kähler-Einstein story, the fact that that you can go back and forth. So just to drive this point home, if I have a Kähler metric of negative Ricci curvature, then the canonical bundle will be a positive line bundle. So that's what we have seen. Now, it's moreover the case that if X is a compact Kähler manifold with negative Ricci curvature, then the canonical bundle is actually ample. So this follows from Kadara's famous embedding theorem, states that a positive line bundle over a compact Kähler manifold is also ample. So take a sufficiently high power of the canonical bundle, the sections of that will give you an embedding into projective space. Yeah, I'm happy with that. Okay, so let's at least state the Richie flow. The extent to which I want to talk about the Richie flow today will be, well, we'll see. So the Richie flow, if we start from a Kähler metric, then it happens to preserve the Kähler condition, and the resulting flow we refer to as the Kähler-Ricci flow. Now, this is another thing I would like to hear from people in the audience. Ben and I discussed this a little bit the other day. Which is the preferred proof of showing that the Ricci flow preserves the Kähler condition? because no one ever talks about it, and I want to hear what people actually like, what people in the field actually take to be the standard proof. So Ben and I were talking about this. You have the corresponding Monge-Ampere flow, and then you have the uniqueness of Richie flow, and so forth. There's this alternative argument that Ben and I were discussing that wasn't complete, so I'm not talking about that today. Ramiro, do you?
How hard is it to show that Richie flow preserves holonomy?
I have no idea.
I'm not sure. Okay. Because that would be the right proof, right? Kähler is just UN holonomy, and Richie flow should preserve holonomy. I don't know.
That's probably a good approach. Much more general than just Kähler, right?
Mm-hmm.
It seems to me though that maybe that argument, even if it works, is not quite as valuable for other types of holonomy, because a bunch of other examples of holonomy force your geometry to be Ricci flat, in which case the Ricci flow doesn't do anything for you anyway.
No, it only works for Kähler and what is the other quaternionic Kähler? That's it. All the others are going to be fixed. But
yes,
they
so
still preserve.
Sort of a nothing argument. Yes, they preserves the structure, but maybe for silly reasons.
Mm-hmm. Okay, that's good. Thank you for that. That's yeah, it's again one of these things no one talks about, and it's too late to ask people because you should have known it 3 years ago. I just say I'm not a flow person. That's how I get away with it. Okay, so this is so when we look at the Ricci flow, starting from a Kähler metric, resulting flow we refer to as the Kähler-Ricci flow. So we saw that a cohomology class represented by a Kähler metric is referred to as a Kähler class, and the set of all Kähler classes in the second arm cohomology group form an open convex cone, and this is what we refer to as the Kähler cone. Now, if it happens to lie on the boundary of this Kähler cone, then we refer to that as a Neff class or a numerically effective class. And okay, well, let's look at the Ricci flow for a moment. So we take a cohomology classes of both sides of Kähler-Ricci flow, and we see that the Kähler class evolves in this way. But we know that the Ricci curvature represents, 2 pi times the first Chern class of the anti-canonical bundle. So when I have a minus here, that will cancel with the dual. And so the cohomology class flows in the direction of the first Chern class. And so in particular, if we look just at the level of cohomology classes, the Kähler-Ricci flow is flowing linearly. Now, there's this very nice theorem due to Tian and Zhou Chang, which states that if we have a compact Kähler manifold, then the Kähler-Ricci flow has a unique solution, which is defined on the maximal time interval, 0 to t, where t is given by this cohomological condition. So it's the largest t for which you remain in this Kähler cone. Okay, so, and I think there's a similar one for the Chern-Ricci flow as well. But the Chern-Ricci flow this is again, this is a bit of Tian propaganda actually. Tian says that I shouldn't speak, especially on a recording. Basically, the Chern-Ricci flow can be argued to be a non-natural flow because it just tries to hijack the benefits of the Kähler-Ricci flow in the Hermitian setting. Given that he invented his own flow, he has his bias. Nevertheless, okay. So here's a nice little picture, and what we also kind of observe is that the Kähler-Ricci flow, the long time existence of that is equivalent to a cohomological condition. It's equivalent to the canonical bundle being Neff. And again, there's some, we'll see in the proof of the Wu-Yau theorem that we are yet to discuss, that this is what really allows you to set things up. And that's a problem in the Hermitian setting, because you don't really have this cone and things to deal with. Okay, so okay, so sorry, let me just check. Yeah, okay. So the sectional curvature is a function on the Grassmannian of two planes which sit inside the tangent bundle. And in this Grassmannian of two planes, we have a holomorphic PN bundle, which is given by the two planes spanned by U and JU. So we can look at the J invariant two planes, where J is the underlying complex structure. Now, if we restrict the sectional curvature to this PN bundle, then that gives us the holomorphic sectional curvature. And in my opinion, it's the most mysterious object in complex geometry and is the most interesting object in complex geometry. So, okay, so let's kind of give more intuition for this object. So if we have our Riemannian curvature tensor, the Kähler metric, we have a complex structure J, then the holomorphic sectional curvature is going to be given by this. Now, if we express this in terms of 1, 0 vectors, so those are tangent vectors, which can be written as U minus I, J, U, then the holomorphic sectional curvature with respect to a given frame reads as follows. So it's a curvature in this kind of holomorphic direction. Okay. So really what it does is it controls the distortion of holomorphic maps. So if I demand that the holomorphic sectional curvature is everywhere negative, then every entire curve, by which I mean a holomorphic map from C into the manifold, must be constant. On the other hand, if I require it to be positive, then I have the opposite of hyperbolicity. I have some convexity condition, and the manifold is rationally connected, meaning that every map from P1, or any 2 points lie in the image of P1, and here I've just taken it to be C. I can take it to be C connected. That's the terminology here. Okay, so a compact Kähler manifold with negative holomorphic sectional curvature is Kobayashi hyperbolic. Of course, here I've given the definition of Brody hyperbolicity, but they're equivalent in the compact case. While if the holomorphic sectional curvature is positive, then it's rationally connected in the sense that any 2 points lie in the image of a rational curve. Now, in the curvature hierarchy of things, the holomorphic sectional sits in a similar spot to the Ricci curvature, in the sense that the bisectional curvature dominates both of them, and each of these dominate the scalar curvature, but they don't dominate each other. And the relationship between them is quite confusing. So how many more minutes do I have? It's 55 now.
I'd be sure I'd be happy if you kept going for another 5 minutes.
Okay, yeah, I'll definitely be done in 5 minutes. So a stronger, hang on, yes, this is the definition of the bisectional curvature. So a stronger constraint is this holomorphic bisectional curvature condition. So this is where we actually have two vectors, U and V. It's called the bisectional curvature because if the metric happens to be Kähler, it has the Riemannian symmetries, and I can write this as a sum of two sectional curvatures. And now I have this kind of curvature hierarchy diagram. So it's clear that the sectional curvature dominates the bisectional. And I can the only arrow that's not obvious is this one, this one follows from the fact that the Ricci curvature can be written as an average using this type of Berger argument of the bisectional curvature. So this is the third rung of this curvature hierarchy would be the scalar curvature. Okay, so the bisectional curvature is very restrictive as a curvature constraint. And the prototype for this type of remark is the Mori and Wu-Yau solution of the Frankel conjecture, namely that if we have a compact Kähler manifold with everywhere positive bisectional curvature, then it's biholomorphic to Pn. Now, as I remarked before, the holomorphic sectional curvature does not dominate the Ricci curvature. And the mysterious example that a lot of people are interested in kind of figuring out why it exists at all is the following example due to Hitchin, which is given by taking Hodge metrics, by which we understand that to be Kähler metrics with integral cohomology class. You take them on Hertzebruch surfaces, which are P1 bundles over P1. There exist metrics of positive holomorphic sectional curvature on such things, but they do not admit metrics of positive Ricci curvature. Now, why do people care about that? Well, it's because the Wu-Yau theorem states that, in a sense, if you look in the negative analog of that case, then it's not directly true, but it's true up to a variation in the cohomology class. So if I have a compact Kähler manifold, which has negative holomorphic sectional curvature, there admits another metric such that when I change the cohomology class, I change the metric within the cohomology class, that has negative Ricci curvature. And then I can even go to a Kähler-Einstein metric by the Orban-Yau theory. Now, since I know that negative Ricci curvature implies that the canonical bundle is ample, I deduce that negative holomorphic sectional curvature implies the ampleness of the canonical bundle. Now, why is this so important? The holomorphic sectional curvature is not cohomological. So we have a non-cohomology constraint giving us a cohomology conclusion. And this is really where I think things are now starting to sit. This is where Hermitian geometry is really forced to live. And the proof of that is what we're going to talk about next week.
Cool. Thanks very much for your interesting talk, Carl.
Okay.
Does anyone have any comments or questions for Carl?
What about the arrow in the reverse direction there? Is there any implication between negative Ricci and negative holomorphic sectional?
That's what we're working on. We're trying to construct examples.
Yeah.
And non-examples. It's we're even struggling to construct examples of things like negative. Hang on, I need to make sure I don't say something silly. There's a lot of curvature constraints where we're trying to understand, okay, this is negative, but this other thing doesn't have a sign. And for instance, one thing that I've been looking at with Simony de Virio is if the holomorphic sectional is negative, do you have to change the cohomology class at all? Is this actually a different metric? Can you just deduce it? Now, in the specific case of this being an Einstein metric, you can show that in general, you do have, it's not the Einstein metric. There's actually a cohomology obstruction to that, as one would expect. And it's at least for surfaces, you have to restrict to a certain churn slope. So the ratio of the churn classes have to satisfy a certain inequality. But at the moment, it's completely unknown whether this cohomology change has to occur at all.
Is the proof somehow variational? I mean, you construct this negative Ricci curvature metric somehow.
Yeah, you don't. You construct it through well, you have a flow, so you kind of use cohomology arguments to kind of to pull back the curtain. So you deduce something cohomological, you prove ampleness of the canonical bundle, and then that tells you that there's a metric of negative Ricci. If I recall, maybe I'm possibly. Well, good thing I'm not giving a talk on the proof of it.
Is that what you're talking about next time? Or?
That's next week will be the proof of the thing. Yeah, that's next week. That's not this week.
Kyle, could you go back to the diagram with the dominance of curvature notions? What about in the Hermitian case?
In the Hermitian case, it's more subtle. We don't have the holomorphic sectional dominating the scalar. It dominates the average of the sum of the scalar and the altered scalar curvature. So in the Hermitian case, what we're really talking about is the first Ricci curvature, because that's the 1-1 form. But there's been some. I think it's a substantial theorem. So Manchun Lee proved a theorem last year, I believe, which says that you can use the Hermitian curvature flow to prove some version of the Wu-Yau theorem in the Hermitian category, but he has to assume some like non-positivity of the bisectional or something. So it's a big curvature constraint that no one wants, and that's why maybe some people have said, it's not substantial, but he gets a Hermitian flow proof of this theorem, which bypasses the key obstruction, which is cohomology. And that's why I think it's quite substantial.
Do you know which of the HCS he uses?
Yeah, so it's he flows by minus the second churn Ricci.
Yeah, but
which
do you know what the torsion term is, or?
I do not know it. I do not know it.
That's
Not
right.
offhand.
Hmm.
But it's curious that, well, actually, so the Schwartz lemma, which is really the key kind of estimate, that has the second Ricci curvature and the holomorphic sectional, or if you use my curvature constraint, the Schwartz bisectional curvature, then like that's what you need to go through. But the cohomology one is the first churn Ricci, which is not what appears in the Schwartz lemma, which is particularly, I find that interesting. Yeah, I'm not alone. There are at least a couple of other people that find that interesting as well. Yeah.
Are there any further comments or questions? All right, then let's thank Kyle again for a great talk.
Hey.
Thanks for that, Kyle. We're looking forward to hearing more about this next week.
Yeah, thanks, Kyle. Very
Thank
nice
you.
talk.